Alright. So, now with this illustration we can discuss certain theoretical aspects of these errors in hypothesis testing. So, as I said earlier, there are 4 possibilities as listed in this table. The columns contain the decisions and the rows contain the truths. Suppose I look at the first row where H naught is true, there are 2 possibilities. I will fail to reject the null hypothesis and or I will reject the null hypothesis. If H naught is true and I fail to reject the null hypothesis, excellent, that is a correct decision, no worries. But as we have seen in the example, it is not necessarily that I will make this correct decision all the times, which means the probability of making a correct decision when H naught is true and failing to reject H naught is not 1, it is less than 1, and in fact it is 1 minus alpha, because the probability of rejecting H naught when H naught is true is alpha. There are only 2 possibilities. Essentially what you are doing is you are partitioning the space of possible values for the statistic into 2 parts, acceptable region and a critical region. That is why hypothesis testing is also like the classification problem, you can think of it that way. This probability of rejecting H naught when H naught is true is also a risk. Why is it called a risk? Well, let us go to the example of this jury trial, which we talked about in one of the previous lectures. In a court of law, the null hypothesis is always that the accused is innocent. That is the null hypothesis that the judge keeps in mind and the lawyer also keeps in mind, and it is a prosecutor's burden to provide sufficient evidence to show that to prove that the null hypothesis has to be rejected. Now, suppose this person is actually innocent and the judge proclaims the person to be guilty, there is a risk associated with it. In many different ways, it could lead to psychological problems for the person, it is a trauma, of course, there is no doubt. It could lead to a major problems for the society and so on. So, it is a risk, and it is a risk for every kind of hypothesis testing problem. So, it is one type of risk. The other type of risk that we encounter is in the second case when the alternate hypothesis is true, that means H naught is false. And if we do not reject null hypothesis, this is the case when the person is indeed guilty and the judge acquits this person. That is also risk, and we know why, because this person can actually go and create havoc again or commit crimes again. This risk is called type 2 error and we denote this as beta. And earlier when I said when we try to minimize the type 1 error as much as we want to, we do end up unfortunately increasing the type 2 error. They are not, it is not that alpha plus beta is 1, please do not get into that, but there is a relation, it is kind of a water bed effect. If I try to decrease alpha, the beta will increase and vice versa. If I want to decrease beta, then I have to sacrifice alpha. Of course, we have the fourth possibility, that which is the strongest one, that is the person is guilty and the enough evidence has been provided and judge finds the person guilty. That is alternate hypothesis is true, H naught is false and we have rejected H naught, that is a correct decision. So, there are 2 correct decisions and 2 risks, but the strongest one is the fourth one, that is fourth possibility that we discussed, that is correctly rejecting H naught when it is false. Why? Because the default, as we have said, is always a null hypothesis, and when a hypothesis test has managed to detect the falseness of H naught with the evidence that has been provided, it is a very good hypothesis test, and therefore, the power of hypothesis test is characterized is in fact the probability of making this correct decision that we reject H naught when it is false. So, by the relation in the table, the power of the hypothesis test is 1 minus beta. Now, however, when it comes to testing the hypothesis, we ask whether do we specify alpha, do we specify beta. In the earlier illustration, what we did is we specified the critical values and computed the alpha. But remember, I said there is a second approach to hypothesis testing where we specify the errors and then determine the critical value. Now, the question is, should I specify alpha or should I specify beta? If you can quickly understand from the table, alpha is associated with rejecting H naught when it is true, whereas beta is associated with failing to reject H naught when it is false. Now, obviously, it is easier to calculate or specify alpha than beta, because to specify beta I need to know the truth, because it is the probability of failing to reject H naught when it is false. When H naught is false, there are several possibilities. We do not know what the possibility is. All we are saying, for example, in a two-tailed test, we are saying mu is not equal to mu naught. When mu is not equal to mu naught, there are several possibilities. So, to compute beta, I have to again postulate some truth that is different from what is postulated in H naught. Therefore, it becomes difficult, and we will see later on in a lecture in the one of the final lectures, what is the relation between beta, the sample size, and the actual truth. There is a expression that allows us to calculate it, but it is a bit more involved, and as I said just now, by specifying beta, we are actually implicitly saying the truth is something different from mu naught exactly. Instead of mu naught, it may be mu 1. But that is not what we want to get into. What we want to get into is, in the context of null hypothesis, that is anchored around the null hypothesis, we want to specify the type 1 error, because that does not make any assumption about the truth if H naught is false. In summary, specifying alpha is much easier than specifying beta, and that is why in practice you see this significance level being mentioned in every hypothesis testing problem, right. That is the story of the significance level for you. And to further reinforce what we have just discussed, we go through a graphical understanding. Again, a caution, the curves that you are seeing are for the sampling distribution of a test statistic that follows a standard Gaussian, which could be the case of sample mean, or maybe sample proportion, and so on. So, the attention should not be paid so much to the shape of the curve as much as it should be paid to the critical region. What we are saying is, in a two-tailed test, you will have critical regions to the left and right of the postulated value because of the nature of the alternate hypothesis, whereas in a lower or a left-sided lower tailed or left sided test, the critical region is to the left of the postulated value, and in the upper tail test, naturally the critical region is to the right of the postulated value. Now, one thing that should be remembered is this area. In fact, there are 2 points. The area corresponding to the red shaded region is what is alpha. So, let us look at the two tail test here. We have 2 critical regions shaded in red, and we have indicated the areas to be alpha by 2. Is this always the case? Well, no. It is the case only when the sampling distribution of the test statistic is symmetric. That is for the case of sample mean, because the sample follows a distribution. On the other hand, if we have the case of the testing of variability where the distribution is chi-square, the density curve we know is asymmetric, in which case the critical regions are not going to be symmetric. That is, they will not have the same area, the probabilities are not going to be the same to the left and right of the postulated value. How does it matter? Well, it does matter because the procedure that we shall follow in hypothesis testing, as we had outlined, one approach is to specify the critical value by the user, but then you will have to keep computing the type 1 error each time, and the other procedure that is followed that is practiced in a standard way is to specify the type 1 error. So, when I specify the type 1 error which is alpha, I then compute the critical value. Remember this we have here z alpha by 2 and minus z alpha by 2. What are these? These are the critical values. How do you compute this? Well, we compute this with the help of the tables that are given, probability distribution tables that are given in a book, or a more modern way is use software such as R to determine this so called quantiles corresponding to the probability. As an example, Suppose alpha is 0.05 and the hypothesis test is a two-tailed test, and we assume that the sampling distribution of the test statistic is standard Gaussian as shown in the figure, and I want to figure out what this z alpha by 2 is. What we do is we go to R and find this quantile. What quantile do I want to find? What does a quantile give me in R? It tells me if what is this value for a given probability. Remember, if I specify this value on the x axis, I can calculate the probability. That is what P norm, for example, would do. Q norm will tell me the reverse, that is, I specify the probability and it tells me the value on the x axis. Which probability should I specify? The probability that the z statistic will take on any value from the left extreme to this z alpha by 2. That is how Q norm is written. For in any other software package, it may be different. So, you have to watch out. As far as R is concerned, Q norm will give me the value on the x axis for the probability that this random variable takes on any value from the left extreme to up to that value. When alpha is 0.05, alpha by 2 is 0.025. That means these two shaded regions here have an area of 0.025. What I am going to do is to determine z alpha by 2, I go to Q norm and ask for the complementary probability, because I know 0.025 is the area of the red region, and I just now said Q norm looks at the probability to the left, from the left extreme to z alpha by 2, and that obviously is 0.975. So, we ask what is the quantile corresponding to this, and there you go, I get 1.96 roughly which we know 95% probable is what essentially is corresponding to the acceptance region. Since it is a Gaussian distribution, minus z alpha by 2 is minus 1.96. If it was a chi-square distribution, I have to calculate the right and left critical values separately. They are not going to be simply the left critical value is not simply the right critical value with a sign reversed. We will have to calculate them separately. We will discuss that in one of the next lectures, where we will talk of hypothesis test on variability. Let us get back to the discussion now. So, what we have learnt is, for a given alpha or a specified alpha, I can compute the critical values, and the advantage is now I know the type 1 error, that is the probability of rejecting H naught when it is true. Of course, the question that comes to mind is, can I calculate beta given alpha? Yes, I can, but the calculation is a bit more involved. We will not get into that at this moment. We will only qualitatively discuss what is beta shortly in the next slide. Let us complete this discussion on determining critical values by specifying the type 1 error. So, it is a two-tailed test. The critical value is the z alpha by 2. The alpha by 2 corresponds to the area of the shaded region on the right. In a lower tail test, as you have seen, the critical value is to the left and the subscript there is alpha on z. You have minus z alpha, clearly telling you that the critical value is going to be of negative sign. In this case, the critical region is completely to the left, because we are saying when does this arise? When the alternative hypothesis is that of the type theta is less than theta naught or mu is less than mu naught. That means, when the test statistic falls to the left of the extreme value that I am willing to tolerate, which is a critical value, then I reject the null hypothesis, saying that no, if the null hypothesis is true, it is very unlikely that I can get an extreme value such as this. Now, once again here I can calculate the critical value, but the only difference between the two-tailed and the lower tail test is that the determination of the critical value. In this case, the critical value can be computed again by going back to Q norm, but now the probability that I am going to specify is Can you guess? Well, that is 0.05 because that is alpha, that is what is the error specification. So, let us ask what is that. Of course, most of us know the answer. Now, here I do not subtract because subtract it from 1 like I did earlier, because we are looking at a lower tail test, that is something you should remember, and there you go, you get minus 1.65 roughly, right. And you should guess therefore, that in an upper tail test the critical value which is going to lie to the right of the postulated value is going to be plus 1.65. The rest of the story is the same. So, now we know for a given alpha how actually we can determine the critical value. Earlier we raised this question, can I determine beta, that is type 2 error, and subsequently calculate the power of a hypothesis test? Yes, we can. I am not going to show you how to calculate that now. However, I am just illustrating what beta is graphically. We have seen what alpha is graphically, and I am illustrating this for a two tail test, remember that. So, what is this beta? If you recall, we are saying that the null hypothesis is not correct, is not true. The alternate hypothesis is the one that is true. Now, the curve that you see in the red is the PDF of the test statistic assuming null hypothesis to be true, and the curve that is colored in blue is the null hypothesis, is the sampling distribution of the test statistic when the truth is something else. That is, if I had specified the right null hypothesis, then the sampling distribution would have been, or the PDF would have been what you see in blue. So, beta by definition is the probability of failing to reject H naught when H naught is not true, which means the probability of finding the test statistic in the acceptable region when the fact is that the null hypothesis is not true. So, I have indicated now the Z alpha by 2. We know that acceptable cases are whenever Z falls to the left of Z alpha by 2, and therefore, the beta is simply this shaded region in blue, because in all these possible values what is happening, the null hypothesis is not going to be rejected, because Z is going to be less than Z alpha by 2, but we have to calculate that probability when HT is true. What is HT? The true hypothesis, which we have not specified. We have specified a different hypothesis in the form of null. So, it is a conditional probability that we are calculating. Symbolically we say beta is a probability of QT not, in fact, not belonging to the rejection region, belonging to the actually acceptable region when HT is true. So, there is a slight mistake, we will correct that in the slides for you. So, probability of QT belonging to the acceptable region when HT is true, and the power is 1 minus beta. What happens? The Z alpha by 2, suppose I decrease alpha, what happens to Z alpha by 2? It moves to the right, as a result of which beta also increases. If I increase alpha, then Z alpha by 2 would move to the left, decreasing beta. So, that is the kind of waterbed effect, but you should not be led to believe that alpha plus beta is 1, obviously it is not. But what you can see is that alpha and beta are tied together in and this illustration nicely brings that relationship. Therefore, the moral of the story is, as you try to decrease type 1 errors, you will invariably increase type 2 errors. That is the fact of life in hypothesis testing. All right. So, now what we are going to do is, we are going to just simply illustrate these ideas and concepts on one example, which is corresponding to the one population. When we say one sample, it is actually saying one population test for mean. I say Z test because conventionally people talk of Z test, T test and so on, which I am not so much in favor of. The correct way of specifying is what parameter you are testing, how many populations, and then you can determine whether it is a Z test or T test depending on the assumptions that you are making. But some schools of thought believe that the moment we say Z test, the assumptions such as population standard deviation is known, large sample size automatically kick in. So, we will kind of stick to this convention in a half hearted way. So, the goal is to test for the mean of a single population under the assumptions that we have just stated, and the null is that mu is equal to mu naught. Alternate could be any one of this triplet, and the test statistic, if you use sample mean, is your standardized sample mean, which we know under and of course, sigma is known, which follows a standard Gaussian distribution, and then the critical region depends on the nature of the alternate hypothesis and the specification of alpha. And as I have shown, you can use Q norm to compute critical values in R. So, let us take this example of the propellant burning rate. This is kind of a burning example for us in this course. The goal is to test whether the average propellant burning rate, you can say, is different or not, depends on how you put it. Mu naught is 50 centimeters per second, and a null hypothesis is that it is not. And I am not showing you the data here. I have drawn this example from the book by Montgomery. The sample mean works out to be, for a sample size of 25, a random sample of size 25 drawn from the population, works out to be 51.3 centimeters per second, and assume that the standard deviation is given as 2 centimeters per second, which means the variance is 4. Now, to work out the hypothesis test, we go through the procedure. Alternate hypothesis, mu is not equal to mu naught, and we have decided we will use the standardized sample mean as a test statistic, which works out to be 3.25 for this example. Since it is a two-sided test and we normally specify alpha 0.05, but you can also specify 0.01, that is also a common specification. We have just now seen through our previous illustration that the critical value is 1.96, and therefore, reject H naught. Why? Because the observed test statistic is more extreme than what I can tolerate, right. It is 3.25 versus what I am willing to tolerate is 1.96. Therefore, I reject H naught. What this means is, I believe that most likely the null hypothesis is not true. There is no probabilities that I am calculating here, probability of H naught not being true and so on. We are not making any such calculations here. All we are saying is, given the data for this sample size, for this specified sigma and specified alpha, I find that the observed statistic is more extreme than what I am willing to tolerate. Obviously, if I change alpha to, let us say 0.01, I decrease alpha even to 0.005 or maybe 0.001, then the critical value keeps shifting to the right, as a result of which at some point I will end up not rejecting null hypothesis. Here we do not know what the truth is. This is a practical example. So, one question that naturally comes to our minds is, what value of alpha will help me or will end up in the decision, say, of not failing to reject the to reject H naught, failing to reject H naught, that is not rejecting H naught. In other words, how low should the alpha be so that the null hypothesis is not rejected? How do we calculate this? I am sure you must have developed an idea by now. Think about it, it is very easy. All we have to do is find out what is the probability of the area to the right of 3.25, because think that I had found an alpha such that the null hypothesis is not rejected, or you can think of the smallest value of alpha that will end up in rejection of null hypothesis. What would have happened? The shaded red region, the critical region, would have been that alpha, and the quantile should have been 3.25. So, in other words, what I said earlier was actually should be alpha by 2 in fact. So, I calculate the area of the that is the distribution, or the density, in other words probability, to the right of 3.25, and that would be alpha by 2. Twice of that would give me alpha. So, we can calculate that in R, right. So, let us do that. how do we calculate? Instead of Q norm, now we use P norm, and now we ask what is the area to the right of 3.25, because if that I had chosen as alpha by 2, then I would have ended up rejecting the null hypothesis. And the P norm unfortunately now gives me the left probability, the complementary probability. So, what I should be calculating is 1 minus P norm, and that gives me roughly 0.0006 roughly. This is alpha by 2, therefore, alpha is 0.0012, right. So, that is the smallest value of alpha for which the null hypothesis would have rejected. Any value of alpha less than 0.0012 would have ended up in failing to reject the null hypothesis, and that value, the value that we just calculated, is called the P value. There are several interpretations to this P value, but let us look at the definition. P value is the smallest significance level that would lead to the rejection of H naught, and for the example, a propellant burning rate example, it is 0.0012. You can think of this as an observed significance level, because we are determining this after the data has been acquired and after the test statistic has been computed. So, it is something derived from observations rather than a pre-specification. In that sense, the other method where we pre-specify alpha regardless of the data is called the fixed significance level. Here we have an observed or an empirical significance level. There is another perspective to the P value, which is that it is the probability of finding or obtaining a test statistic more extreme than what I have obtained. So, I have obtained 3.25. Is there a probability that I can obtain more extreme than this? Yes, and that probability is 0.0012. What is the use of that? Well, that tells me how extreme the value that I have obtained is. If look at this example that we just had, we said the value is 0.0012. That means there is a 0.12% probability of obtaining a value more extreme than this. What does this tell me about the observed value? It is a very less likely value when the null hypothesis is true. So, P value is calculated assuming the null hypothesis to be true, remember that. What if this P value was very high, was quite high? That means that the probability of obtaining more higher values or more extreme values than what I have observed is large. When would that happen? When the test statistic has fallen into the acceptable region. In fact, we can use this P value, which is what is done widely, is practiced widely. I can use this P value to determine if the null hypothesis should be rejected or not. How? I compare the P value with the fixed significance level, that is, let us say 0.05, and if the P value is greater than alpha, then obviously it means that the test statistic is in the acceptable region, and if the P value is less than alpha, then clearly the test statistic falls in the critical or the rejection region, and I can therefore say reject H naught. So, now you can actually use P norm or PT or P chi square and so on to compute your P values. We will cite P values whenever we go through a hypothesis test. That is the story of basics of hypothesis testing for you. We have in this lecture learnt what are type 1 and type 2 errors, that they are closely related. If you try to reduce one, the other shoots up. That is a very important thing to remember. Of course, the definitions of type 1 and type 2 error, we have gone through a few illustrations, and we have also discussed what is meant by power of a hypothesis test. More importantly, we have also learnt how to determine the critical values when a significance level is specified a priori. And we have also learned the concept of P value, which is the observed significance level, which helps me making certain decisions. That means, it tells me how far I could have gone, the process could have gone before the null hypothesis is rejected, or what is the minimum level of adjustment that I have to make in order to actually bring back the test statistic into the acceptable region if the null hypothesis has been rejected. So, it is quite useful to the manufacturers or process design people. And also let me tell you, there is a fair share of criticism of the use of p value, but then this criticism depends on how you use the p value. If you truly understand the definition of p value and where it should be used, then you are not subject to that criticism. A researcher's duty is to point out what are all the areas in which limitations of a certain measure and what pitfalls are associated with the use of either p value or alpha and so on. So, one has to be aware of this and learn essentially the definition of those measures like p value or type 1 error and so on, and also know when and how to use them, and that is what is one of the primary purposes of this formal course on hypothesis testing. What we will do in the next lecture is we will go through a set of examples and the hypothesis test only associated with mean. Remember, we had so many different situations when we talked of sampling distribution of sample mean. We will essentially cover all those cases, and then in that subsequent lecture we will look at the tests on variability, proportion, ratios of variability, differences in proportion. With that, we would have kind of discussed whatever we want to talk about the traditional way of hypothesis testing. The last unit the last unit will tell us how to conduct the hypothesis test using confidence region concept, confidence interval concept. That is a very beautiful concept, and in one of the lectures in this unit we will also learn, again come back to the hypothesis test and ask what is the relation between sample size and the type 2 errors in the hypothesis test or the power of a hypothesis test, where we will learn that there is an inverse or there is a direct relation. As we increase the sample size, the power of a hypothesis test typically increases, which is encouraging, which means it is telling that collect more and more samples, so that you make as less type 2 errors as possible. We will learn those relations and also learn in all of these next lectures, we will learn how to do things in R. We will discuss a theory and I will show you how to do it in R, and I will give you a list of commands as well. Okay then, so hopefully you enjoyed this lecture. We will meet again very soon in the next lecture. Thank you.